Hello, 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 hello. This is Concrete Path. Today, today we are going for the deflection of beams by using different methods. But before that, we had few problems of shear force diagrams and bending moment diagrams. So for that, let's go and solve a few problems for shear force diagram and bending moment diagram. So you got a frame with an inclined member and simply support that hinges support here and a roller. Add D, you got A here. You got a uniformly distributed load that, but your member is inclined member. Your member AB is inclined, so the length along the horizontal is 4 meter and height is 3 meter. And you got one more point load here at equally spaced between B and D. That is 2 meter and 2 meter. You need to get the shear force diagram and bending moment diagram. The loading intensity equals to 40 kilonewton per meter. So first step is that get the reactions. Let's say the reaction here is reaction D and the reaction here is reaction A, and the horizontal reaction here would be that summation fx equals 0. Then we have 40 into your length 3 meter, that equals to your reaction horizontal A 120 kilonewton. And now if we do summation of moments about your point A equals 0, we can say D into your anti-clockwise moment about A about into your length of 8 meter. Then after that you had clockwise moment of 180 into your 6 meter. Then after that you got, because of the UDL, so we can write clockwise moment of that 40 into your 3 meter, and it acts at the centroid, and we can write 3 by 2, that equals 0. So your reaction at D becomes equals to, that becomes equals to 82.5 kilonewton. So we can write that summation Fy goes to 0. Then we can write A would be equals to that 80 minus 82.5 equals to minus 2.5 kilonewton. So if we want to make that free body diagram, we can say your member, for the member AB, this is your we can go start with the that easier one, your that beam. So this is your beam. We got the reaction of 82.5. So we get right 82.5. Then after that we had a point load of 180 kilonewton. So here the reaction, we can say here would be some Vx and here would be some Mx. We can calculate those values. Say this is your 2 meter, this is your 2 meter. We can write 82.5. That I can write summation mx equals to 0. Summation of moments at x equals to 0. Then we can write bending moment at x clockwise plus your 180 into your 2 meter. Then your minus 82.5 for length of 4 meter equals to 0. So your moment at x becomes equals to that 170 kilonewton. 170 kilonewton meter. Then similarly we can write shear force. Here would be the difference of the two transverse forces, 180 and 82.5. So net value of that we can write summation Vx upwards plus 82 upwards, and your downward of 180 Is it 180? No, it was that, it was your 80 kilonewton. It was your one that 80 kilonewton. This was your 80 kilonewton, and we can write that equals to 0. So your shear at x becomes equals to minus 2.5 upwards, minus 2.5 downwards, minus 2.5. We got negative. That means your shear here is downwards. So we can keep it downwards, downwards 2.5. Then similarly we can write that shear was here negative, and we can write positive here value 2.5. So accordingly, now we have calculated all those forces in the that member BD. And we have that member AB. So this is your member AB, and what we have here, we have the that we have that the moment here was developed equals to that some value we got, that 170 kilonewton meter, 170 kilonewton meter, 170 kilonewton meter. So those same forces would be, same forces and moments would be transferred into the member BA. So we can write that if it is the moment is in the BD clockwise, here would be anti-clockwise moment of 170, and here the reaction was downwards V equals to 2.5. Here the reaction would be 2.5 upwards. And after that we got that loading, we got that horizontal loading, that was equals to 40 kilonewton per meter for a length of 3 meter, and the horizontal was also at 4 meter. And we can say that uh, the vertical force here would be downwards 2.5, and the moment here, because your because your support is hinged, so your moment at the hinge support would be 0. If you can also check that, you can also check that by that say here the moment is m, we can write m0 because moment is 0 here. We can write moment 0, moment 0 will your anti-clockwise plus 40 into 3 into 3 by 2 clockwise minus 170 170 anti-clockwise plus your that 2.5 for a length of that 4 meter equals to 0. If we calculate the value, we can say that 9 into 0.5 into your 40 minus 170 minus 2.5 into 10. So minus 15 value, it comes 40. That minus we said that it is your anti-clock minus m naught, then we had clockwise 40 into 3, 40 into 3 acting at 3 by 2, then we had your that minus 170, and we got also minus 2.5 into length of 4 meter. So that you're right, 40 into 9 by 2 minus 170 minus 10. Yeah, we got the value 0. Moment at hinge support is 0, we know that. It was a check, can write it. It was just a check we made. So finally we got the forces in the that members. That if you want to say for the shear force diagram, we can make the shear force diagram for this member. We can easily make the shear force diagram for this member. We can make the shear force diagram. We can say that shear force diagram would look like this one, and bending moment diagram would be this one. And we can say your shear force is negative downwards. That means here the reaction was downwards 2.5, so reaction would be, that shear force diagram would be negative 2.5. Then it would remain constant because there is no external force after this point. Then after that you had drop of 80 kilonewton. When you have drop of 80 kilonewton, then we can get the value finally equals to 82.5, and here the value is 82.5 upwards, so we can get the final value going to 0. So this is your shear force diagram. For the bending moment diagram, we can have, say, here the external, here that moment that was developed at that joint, it was 170 clockwise, so your 170 clockwise is there. This is your 170 clockwise positive. Then after that we had the area under the curve up to the point that 2 meter. We can say here would be some value that 170 and negative value of that 2.5 into your 2, one that would be coming out to be 160, 165 something, that 165. So the slope is like varying a little bit because your variation is just a 5 that 5 kilonewton meter, so your value here is 165. Then after that we have a sudden change in, or we can say a kink in BMD. Now here would be a kink in BMD. A kink in BMD means a change in slope. Now see here the slope was that minus 2.5, but here the slope would be 82.5, so we can join the two values, 2 points, that here would be the value of that minus 82.5. we can yeah, here in this part, in this part we can say shear force is negative, and shear force is negative and constant. We can say for the bending moment slope will be constant and negative. So your BMD for this part, but the case is that we can't get the shear force diagram for this part because your member is inclined or your loading is inclined, because your loading is inclined. So we need to get the those components of the loading that perpendicular to your section or transverse to your section, that we get if the transverse means you can get that perpendicular to your that member, that means your shear forces, and similarly we can get the axial forces also. That so for that we need to get the resolution of those force vectors. So let's have those vectors that we have that three vectors here. One is your horizontal loading, next one is your vertical loading, next one is your loading that's UDL in the horizontal direction. So you'll be solving those values, that resolution. Now we have that theta equals to that. This is your theta, so we can write that this is your 3 meter and this is your 4 meter, 3 meter and 4 meter. So we have that, let's say this is one member and that load is acting 2.5 downwards. Here the theta, it is your theta, so we can write that. So this is also theta, so this is also theta, so here would be 2.5 cos theta, here would be 2.5 sine theta. Similarly we have one more force, that is a horizontal of 120, that horizontal reaction of 120 kilonewton at spot A. So 120 in the negative x-axis, so we can write that here it was that 120 kilonewton horizontal, so this is your 120 kilonewton horizontal. Here that value of theta, and this is also theta. So your component, so your component, so your component in the transverse direction to the your member AB is that it would be a 120 cos 90 minus theta, that is 120 sine theta, and in this direction it would be 120 cosecant theta. So next member is your, since your UDL is also that it's not in the perpendicular and horizontal direction to the member AB, we need to resolve the that UDL also. Say the UDL is, say the UDL is that, say this is your member, say the resultant of the UDL is also a vector at the centroid, so we can say the resultant is passing through the centroid, that at the that at 1.5 meter, that this one, and they need to pass here somewhere, so we can say here it is also theta, it's also theta, that means your the force here is 120, so your component along that member would be 120 cos theta, 120 cos theta, and and uh, and let's make it the member make it a little bit tilted, then make it tilted. It was somewhat this way. So the member force along the line along itself, it is 120 cos theta, and in the perpendicular direction are transverse to the member, it would be, say, this one. So your force would be downwards 120 that sine theta. Now we have the values of sine theta and cos theta. Sine theta equals to that perpendicular is your 3 meter, horizontal 4 point, that perpendicular by horizontal, that hypotenuse, that is 3 square plus 4 square, that is 0.6, and cos theta equals to 4 by 5, that is 4 by 5, 0.8. After you add the results of those three, you would get the final resultant values of that. See, say we got the values, say, for the that UDL, this was for the UDL, that then it was your equivalent 120, equivalent 120. So finally we got the values that 120 cos theta is your 120 cosecant theta, that comes out to be equals to 96, and 120 sine theta equals to 120 that 120 sine theta that equals to 72 kilonewton, 72 kilonewton. So this is the total load that's acting on the entire that 5 meter span. So it's acting on the so your two member forces are acting on the that your member. So to make it an equivalent UDL, because your load was also UDL, to make it equivalent UDL in the transfer direction to the member, that AB was your 5 meter, so you need to make an equivalent UDL, say 72 kilonewton is transverse force, then it has to be divided in 5 meter, then we can get the equivalent UDL of that. It comes out to be 14.4 kilonewton meter per meter, and along the actual that along the axis of the member, you also get one that equivalent load of that 96 by 5. 96 by 5 equals to that 19.2 kilonewton meter per meter. So you got one more force that's along the actual line of the member, that's 19.2 kilonewton meter, and after doing the summation of these other two forces, one is your downwards 2.5 cosecant theta in the transverse direction, next one is your upward 120 sine theta. So you solve the values, you would get the resultant value here somewhat equals to 70. You get the value here 70, and along the axis we got value of 97.5. Then you got the UDL of that 19.2 for the length of 5 meter. Then we have that we can get the resultant value here say we don't know the value of some, say we want to check now what's the value of that force along the axis here, and the shear force here also. And your there should be there would be some net moment, because the moment here was 170, so the moment here is also 170, and it should be 170. It should be 170. So if we want to, if you want to calculate now that how, what's the effect of that, uh, that if you calculate now that summation of forces in the member AB along the transverse axis, so we can say summation of forces in member AB that's perpendicular to it, that's your shear forces, so we can say equals to 0. Then we can write that here the reaction is say VB, so we can write that 70 upwards plus 14.4 into phi length, then we have upwards VB, so your VB comes out to be equals to that -2. Yeah, this was downwards, so we get the value of that +2 kilonewton. That means upwards +2 kilonewton. So then we have the shear force, that the axial force, that is, we can write summation of forces in the member AB parallel to it. That's your axial force. That means your 97.5. We keep it negative, that is downwards. Then after that we had, or we can keep it tensile, that away from the member, and your axial force of that UDL 19.2 into your 19.2 into your 5 meter, that's 96, and your, then you assume that some horizontal would be there. Horizontal B, say that is horizontal B is also upwards, so we can write positive that negative equals to 0. We can get horizontal value of that 96 minus 97.5, that's 1.5, 1.5 upwards. Then we got those values. If we want to check the moment also, you can do that 70 into your 5 and your UDL into your 5 squared by 2. So finally we got those values of that shear force and bending shear forces and this axial forces. So if you want to make that diagram, we can have the diagram. So this is your member. We got the shear force value here, that equals to 70. That equals to 70. So this is your 70 kilonewton. 70 kilonewton. Then after that, the shear force at point B is upwards to. That means there should have been, the line should have been gone down by amount of 2, such that after that point there would be a reaction of 2 at point B. So if we also want to calculate that, we can say you can calculate that by saying, we can say 70 plus your UDL of 14.4 into your length of 5, that's minus 14.4 into length of 5. We can get the value of shear force at that point 2. So we can get the value of shear force at point 2, that comes out to be minus 2. So we got the shear force of this part, and we already got the shear force of this part also. So to make it a combined one, let's join. Let's say this is your member one, BD member. So the loading was that, because of that loading, we got that shear force. We got that shear force diagram, that negative 2.5, negative 2.5. The shear force diagram is perpendicular to the member. That 2.5. Then after that, it was linearly constant. Then after that, you had 82.5. So this is your shear force diagram. 2.5, 82.5. Then to make the bending moment diagram for this part, we can have why is the loading? So say this is your this is your member this is your member AB. We have the here the support was that hinged support, so the moment here is 0. Then we had a 170 kilonewton that that anti-clockwise moment on the left side of the section. So if your moment anti-clockwise on the left side right side of the section, that is positive moment. You can also that check that from your that loading diagram, because your shear force diagram is positive. That means area the area of the shear force diagram is positive. That means your bending moment would be positive. We can write that moment, say moment here. We can calculate the moment here. That's your we want to check what is the value of shear force here. At that point, maximum that moment would be maximum. Bending moment would be maximum. Bending moment is maximum here, so we can calculate the value of that point here. We can say the shear force here was 70. So 70 is varying. 70 is varying in your length. That in say this is your length x. So 70 is varying in your length x, and your shear force downwards too. It's varying in your length 5 minus x, and we get the value of x equals to that 70 by 14.4. Or we can say that 70 shear force is changed because of the UDL acting. So we can write that 70 equals to 14.4 into x. So we get the value of x equals to 4.861 meter. 4.861 meter. 4.861 meter. Then that means your bending moment at this point 4.861 meter. So this is your 4.861 meter. Bending moment here would be a positive value, that because your shear force is positive and decreasing, that means your bending moment diagram is also positive, and that means your slope of the bending moment diagram is also positive and decreasing. Say it is decreasing, like decreasing downwards, so that slope here is say maximum. At the maximum, slope is 0, and it is a 2-degree curve. Here the slope is positive, that 70, because your shear force is 70 kilonewton. 70. The value of that bending moment here would be equals to area of the SFD up to the point that point x. We can write half of that 70 into your length. X was equals to that 4.861. We can get the value equals to 170.135. 170.135. After that, we had a negative shear force area, that negative shear force diagram for the length that 5 minus x. That's very small value, and if you calculate that, and your shear force diagram at that point would be now equals to finally 170. 170. Here the value is 170. Now actually it's at the end, so your diagrams looks like that. At the end, your value of that shear force, that bending moment is 170. So you need to join the two that you need to connect the 2 points. That this is your bending moment diagram, positive bending moment diagram for your member AB. It should be 170, because that joint equilibrium has to be maintained. That if your moment in the in your span BD was at the joint B was that 170, in the clockwise direction it was your positive 170. In this value it should be anti-clockwise 170, but it is on the left side of this, it is on the right side of the section, and say it was your section B. Here it is in the clockwise direction, so it's your positive bending moment diagram in this positive, and here it's also positive. So then if you join the two, if you combine them, you can have a curve somewhat like this. Then we have that maximum value of that bending moment here at x equals to that value of where shear force was 0, from increasing slope to from slope was maximum here to decreasing slope. Finally we got some value here, and it was then it changed a little bit such that the final value is 170 kilonewton meter. Then after that, in this part you had that 170 also, 170. This is also 170. Then it changed it to 165 here, a linear variation. After that, it had a change in slope because of the shear force diagram. Area was very much 82.5 that. So this is your bending moment diagram. We can add this one is your sagging, and this is also sagging. Then we have one more question on the frames. Let's take that question. That you got that 5 meter here and a fixed support. After that you got 1 meter, you got this 1 meter, and you got this 2 meter. Then you have a UDL of 4 kilonewton per meter for length of 2 meter. Here is the point A, B, C, and D. We need to get the shear force diagram and bending moment diagram. So if you calculate that, what's the effect? We can directly say that we can make free body diagrams, or we can initially start by the reactions. If you want to say start by the reactions, then you have to follow you need to get the reactions first. But on the other hand, if you want to solve it directly, because you need to, after solving the reaction, you still need that free body diagrams. So if you start from the direct free body diagrams itself, it becomes that easier. Let's say your member AB. Let's say this is your member AB. You have a loading of that 4 kilonewton for length of 2 meter. So the reaction here would be upwards shear force of that 8 kilonewton, and the moment developed here would be, say, because of this UDL, it's acting for 2 meters, so your force of 8 kilonewton meter acting at 1 meter from this section. So it's trying to make a clockwise moment. So here the moment developed would be anti-clockwise moment of 4 into 2 into 2 by 2. That's equals to 8 kilonewton meter. Then after that, there's no horizontal force in the member CB. This is your member CB. Here the actually that vertical load was 8 kilonewton, so it becomes axial force in this member 8 kilonewton. And after that, it has to be here 8 kilonewton upwards. So it's a tensile axial force in the member BC. Then we have that we were having a clockwise moment of we are having a anti-clockwise moment of 8. Here the moment would be clockwise moment of 8. Clockwise moment of 8. Then after that, since in the part BC there is no external load, so to balance this 8 kilonewton meter about this point, there should be some 8 kilonewton that opposite to that, so that final value, that moment equilibrium is balanced, is achieved. So it's a positive bending moment diagram also. Then after that we have that cantilever. We got that cantilever. Say this is your 5 meter. Now the actual force was 8 kilonewton meter. 8 kilonewton. Here the actual force that transferred here would be it becomes here shear force of downwards 8 kilonewton. Then you had that 8 kilonewton acting anti-clockwise. Here the moment would be clockwise 8 kilonewton meter. Now we can directly say that now what is the value of bending moment here? We can say that horizontal would be 0, but the here the shear force would be 8 kilonewton upwards, and because of these effects, say the moment here is m, say the moment here is m at d, we can say summation of moments at d equals to 0. We can write minus md bending moment at d, and we have minus anti-clock 8 into 5 meter. Then we have clockwise moment of 8 kilonewton. That's positive. We can write that moment at d equals to a negative 32. Negative 32 means clockwise moment of that minus that 32. So we got that value of 32. Now to make the shear force diagram for this member, you can say this is your shear force diagram. Here it is 80, here it's 8. So we can write shear force diagram of that downward value of 8 kilonewton. After that, there is no external load, and there is no effect of concentrated moments in your shear force diagram, so it remains constant after the point where the member is joined to your support D. So value of 8 kilonewton SFD. Then after that we have the bending moment diagram. So this is your bending moment diagram. Here the moment was acting clockwise moment of 8. That's your positive 8, positive value of 8. Then there was no, yeah, then after that you have shear force diagram. That's area of the shear force diagram. Area of the shear force diagram equals to that 5 into 8, that's 40 minus 40. So finally you get the value as here you get the value as that if the value here is 8, you get the final value here is minus 32, because we can say m2 minus m1 equals to area of the shear force diagram. So your value becomes minus 32. That's equals to that moment at D. It was also minus 32. That means it was clockwise. So if your moment is acting clockwise in the right side of section, that is negative moment. So the variation, since your shear is a function of x power 0, so the bending moment diagram would be a linear variation of x. So we can join the two values. So 32 would be somewhere downwards, because 8 is less, so we can have line here. So the point of contraflexure, this is your point of contraflexure. You can write it value is equals to 8 by x equals to 32 by that 5 minus x, and the value of x we have not calculated. We can get the value of x also. So this was your shear and bending moment diagram for this member, cantilever member. Then we have that axial member, that there would be only an axial force of that tensile. So we can write it as positive. This is your positive axial force diagram for this member. And if you want to make the shear force diagram, since there is no transverse force that's perpendicular to this member, so we can write that shear force diagram is this one, shear force diagram. And bending moment diagram, we can write your clockwise moment of 8. So your clockwise moment of 8, that is positive. That's your positive. Then it remains constant because your shear force diagram is 0. Then it comes to the point B, where the shear moment of that clockwise moment of that 8 also there. So finally you get the value that 8 kilonewton meter positive bending moment diagram. And for the third member, you have that you can write shear force diagram looks like this: 8 upwards, 8 kilonewton upwards. Then you change by that intensity into your length x. So your shear force at the end would become 0, because you can write that shear 2 minus 8 equals to your UDL of minus 4 for length 2. So you got the shear force 0 here. So the slope here is 0. Here the slope should be 0. So you have to join. So slope here should be 0. Now, since your UDL is the slope here would be minus that W, slope here is also that minus W, because loading intensity is constant. If your loading intensity is constant, that means your shear force diagram slope is also constant. And your loading intensity is negative. Loading intensity is negative. Uh, um, your loading intensity is negative. That means your value of slope is also negative. Yeah. So we can say that in that shortcut we can say loading intensity is if the value of loading intensity is negative, that means your shear force diagram slope is negative by the relation dv by dx equals to uh, loading intensity, slope, and loading. So if your loading is negative, that means your slope is also negative. And after that, if your loading is downwards, if your loading is downwards, or if your loading is downwards, nah, if your loading is constant, we can say if your loading is constant, that means your slope is also constant. Finally, we have reached to the point. Now we have to get the bending moment diagram for this member. This member is your, say your moment was developed here anti-clockwise 8, anti-clockwise 8, and after that you need to get the that shear force diagram area, half of that 8 into your length 2, so you get the value at as 8. This was your minus 8, and you need to add plus 8. Then this is your 1 degree, so the BMD would be 2 degree. Then here the slope is 0 in the bending moment diagram, because your shear force is 0, and the slope here is equals to that plus 8. So joining the two, this is your BMD. So final BMD and shear force diagram would look like this one. This was your shear force of 8 kilonewton. Here the shear force was 0, and in this part shear force was positive. Then see, to make the shear force diagram in this part, you have to see in this direction. Uh, in this direction, say we have to make that bending shear force diagram actually like this, that you are seeing inside the frame. If you are seeing inside the frame, that means the loading diagram would look like this one. Loading is acting downwards, so in your direction loading is acting uh, you are seeing the diagram. You are seeing the that AB this way, such that loading is that upwards, and your shear force value that at the end it was 8, reaction was 8 upwards, so you are seeing it as 8 is going downwards. So to make the shear force diagram actually for this section, we have to make this way, that this is your SFD minus 8, but the value is positive, positive. We got the value as positive diagram, that but to make it, we can show it in the downward direction, but its value is positive. That's to make that confusion clear, that uh, whether we should make a diagram up in upwards or in here, but just you have to make this that positive or negative. Rest is concepts on the. If you want to make here shear force diagram here also, there is no problem, but you have to make the sign also that it is positive value of shear force. But we say that generally we go that we when we analyze the frame, we sit inside the frame. For this part, we see this as a beam in this direction, this one in this direction, and this one in this direction. as we earlier saw, there's those beams. Then after that we have to get the bending moment diagram. We already got those values and we can combine them. Here the bending moment value was 8 positive, sagging positive, then it was minus 32, and join the two by straight line. And in this part there was no shear force. There was no shear force. But was there any bending moment? We had, see, if to maintain the joint equilibrium, if here a bending moment of 8 is there and it is, say, clockwise, here it should be anti-clockwise. So positive value of 8, bending moment, and it should be constant because your shear force diagram is constant, is 0. So your bending moment diagram would look like this one. And after that we had a moment of that, what we got equals to that -8. -8 is shown inside the frame, that -8, say this is your -8, then after that you have to join that. Here the moment is 0, then you combine the two. This is your negative hogging, this is your 8. So this is your final BMD for this member. So we have one more question that uh, we have SFD given, shear force diagram is given, say a beam of 8 meter. Here the value of that. Here the value of shear force is 195. Then it reaches to 165. 165. 165. In 6 meter length, it reaches to 165. This one is your 165. Then after that, you have a sudden rise of, such that the final value becomes positive 120. And after that, you have 2 meter length, so finally becomes 0. This is your shear force diagram. Here the value is 195. Here the value is 165 in 6 meter length. And this one is your 2 meter. And the value here is 120 kilonewton. So we need to get the loading diagram and bending moment diagram. And there is also mentioned that no couple is applied anywhere. No couple is applied anywhere. Earlier we saw that there was some equivalent, some net bending moment developed. So to balance that, we said that there should be some that couple to be applied anywhere. In this question, it's mentioning there is no couple applied. So we need to see what's happening inside. So we can say, what is the value of this point? We can say this is the value of x. We can say 195 by x minus equals to 165 by 6 minus x. You get the value of x. And after that, we can have that bending moment diagram here to be maximum. So initially we can solve for the loading diagram. We have that since your shear force diagram is varying, shear force diagram values are varying, so we can say change in shear force in your length L equals to loading intensity. So we can write V2 minus V1, but your V2 is negative, V2 minus V1 in your length 6 meter. That's your loading intensity. So it comes out to be equals to 60. Is it 60? 60. Yeah, 60 kilonewton. 60 kilonewton per meter. That's negative, means acting the loading is downwards. So this is your loading intensity. We can make the loading intensity at the top. See, since there is a sudden that at the end there is a sudden rise of 195 in the shear force diagram. That means here it should be some reaction of 195 upwards. Then after that we got the UDL of that 60 kilonewton per meter for a length of 6 meter. Then after that we have that dv equals to minus p. So we write that change in shear forces from 120 to minus times that minus 165 equals to minus p. So your shear force becomes that. So the value of p becomes equals to minus 2 times 285. That means the direction assumed is wrong. That means the reaction has to be upwards because your shear force is going upwards. So your load is acting upwards. There should be some support giving direction of 285. Reaction of 285. Then after that we have a variation that shear force changes from 0 to 120 in your length 2. So your loading intensity is also minus 60. So your loading of minus 60 for the entire span, and your now we want to say that either we know that if the loading diagram is drawn from the shear force diagram, it always satisfies your force equilibrium, but it may not satisfy the moment equilibrium. Let's say we want to check the moment equilibrium. Let's say we want to see whether the moment here is balanced or not. Say this is your point A. Want to check the summation of moments at point A equals to 0. Then we write that UDL of 60 into your length is 8. Then it acts as 8 by 2 clockwise positive. Then we have negative 285 for length of 6. So if you calculate it, you get the value somewhat equals to 210. That means the moment actually it was clockwise and this was anti-clockwise. So you get the value as plus 210 kilonewton meter. But so the moment is not balanced. Moment equilibrium is not achieved. To make the equilibrium achieved, we have two supports. We can say that since there's no couple applied, there is no external concentrated moment to be applied anywhere. So we can say there should be the support A should be a fixed support that it would give reaction of anti-clockwise 210. So let's say take A as fixed, and such that moment A equals to 210. That's minus 210 kilonewton meter. That's in the anti-clockwise direction. So to make the now bending moment diagram, we can say this was your minus 210 downwards. This is your minus 210 acting downwards. Then after that we have that positive shear force diagram up to this point x. We have to get the value of x. Your x value becomes equals to 3.2 feet, 3.25. We can write that the value of bending moment here would be that minus 210 plus 1 by 2, 195 into your x value of 3.25 into 0.5 into 195 plus 210. That's equals to 526.87. But first one was negative, so we had to make the sign also there. 106.8750, 106.8750, 106.8750. So this is your positive value of say this is your 106.8750, 106.8750. Since your slope is that shear force is 0, that means your the slope of the slope of bending moment diagram is also 0 here, and we have to join the two. Since your shear force is a linear variation of x, so your bending moment diagram is a linear variation of is a square variation, that x square of that x. So we have to combine, we have to join the two such that your slope here is equals to the shear force of 195, and here the shear force is 0, so join the two. Then after that we have to get the value of bending moment here, so we can write that. Now we got the value of 106.8750. I want to check moment 2 minus moment 1 equals to area of that SFD. This is your negative SFD area, 165, into your length was that 6 minus x. Then the value comes out to be equals to that 165, 120 kilonewton meter. 120 kilonewton. 120 kilonewton meter. And we have to join such that the slope here is 0 and the slope here is 165 negative, and you join the two. Here the slope is 165 minus, and now we want to check the moment here. Since it was your free support, there was no support there, we can write the moment should be 0. We can also say that the variation is shear force variation is 1 degree, so your bending moment diagram variation is 2 degree. So this is your bending moment diagram. So there are 2 points of contraflexure, 1 and 1. We can get the value of contraflexure here. Can we get? we have the loading, general loading, that we have the general loading. We got 2 contraflexure points. So we can have that equation. So we can write, let's say this is your 195, and here the loading that moment was 210, and say this is your loading intensity. But we got that from the bending moment diagram, that just before that 6 meter, just before 6 meter, you got 2 point of contraflexures, 1 and 2, but just before 6 meter. And if we see just that just before 6, there is no effect of this concentrated load. So if you want to write the equation, that is the entire equation, that bending moment equation is valid for the entire section till just before of that 285. So we can write that equation, that if you go from that x, we can write the shear force here is Vx and moment here is Mx. We can write that summation of moments. We can write that minus Mx, then minus 210 minus then 195 for the length of x, 195 into x. Then we have that UDL of 60. That's also anti-clockwise, 60 into x squared by 2 equals to, well, that summation of moments. But we say that we want moment x to be 0. We want bending moment. We want for bending moment to be 0 and x to be 0. We write that bending moment at x. So this is your bending moment at x. This is your bending moment at x. We can write this is your bending moment at x has to be 0. So we write that summation of moments at x equals to 0. This is your moment equilibrium condition, and this is your condition that bending moment has to be 0. Bending moment has to be 0 because these are your point of contraflexure. So this, we want this also to be 0. Initially this was summation of moments at x equals to 0. This one is your bending moment at x equals to 0. So by writing that, we got the quadratic equation, and we get the values of x equals to 2 values of x, that's 5.137 meter and value of 1.362 meter. So these are your 2 values. Just show the values that this is 1.362 and this one is your 5 point something, 6 point something, 5.137. So this was your final diagram. Now after that, we got one more question, that say this was your simply support beam, load is acting at center. We say that the shear force diagram looks like this one, and the bending moment diagram is your PL by 4, and this is your P by 2 if your length is total L. But let's say that the load is not acting at a concentrated point. Say that take example of a column. If it's mentioned that column acts for a length of say x, then make the shear force diagram. Say this is your column. Usually the column length, column width is say 500 mm. Say this is your x, and the total load of the column is transferred at the center. So this is your P. So then after that you got this is your beam of length L. Now if you want to make the shear force diagram, you would say here the reaction is P by 2. So the reaction here is P by 2 and the reaction here is P by 2. Then so we can say that shear force diagram looks like this one. Up to this point, we can treat it as UDL of that. UDL equals to P by X. So we can say we want to check the shear force value at this section. So we can say at this point shear force would be equals to that UDL intensity. We can write here the value is P by 2. We can write V2 equals to V2 minus V1 equals to add up the SFD between the 2 points. Add up the loading diagram. That's add up the loading diagram is itself equals to W into X. That equals to P. But it's acting downwards, so we're at minus P. So final value is minus P. That minus P by 2. So your final value of minus P by 2. That was also here minus P by 2. But the thing is that the thing is in this part you have variation of that. If your shear force since in this part there was no external load, so your shear force remains constant. But in this part there is a UDL intensity. We have that dV by dx equals to W. If your loading intensity is having some value, constant value, that means your shear force diagram is a linear function of x. Since because your loading intensity is like this one, that is your total load of P in your length x. We can say your loading intensity is not a function of x, but your shear is a function of x. So we have to join the two by straight line. So this is your final shear force diagram. And similarly, if you want to make the bending moment diagram, we can say up to this point we know the value that this is the value of bending moment here would be that the area under that curve, that's that's P by 2, that's P by 2 into your length, that's L by 2 plus this one would be x by 2. So we can write L by 2 plus x by 2. Then similarly from this side there would be same value of PL by 2 plus x by 2. Then after that, what is the value of that this curve? It would be a 1 by 2 P by 2 and x by 2, and you had to add that value to this value, so that the final, since the slope here, since the shear force here is 0, that means your bending moment slope is also 0, and since your shear force is 0 here, that means that's dm by dx equals to 0. That means your m is maximum of a constant value, that's maxima. So we can get here it's a 2 degree part. This one is your 1 degree part, this one is your 2 degree part, and you can join the two. This value we can have that PL by 2, that P by 2, L by 2 plus x by 2 plus that Px P into x by 8, P into x by 8, 1 by 2 into x. Yeah. Next one, we have that, let's say this is your, let's take that this is your, let's say this is your rectangle, this is your B and this is your height h. Now what is the thing that we have that parabolic, that those two types of spindle. If we have that, let's say here the if you cut those two, here it should be 0, here the theta should be 0, then if you want to say these are your parabolic those curves, this is your if you want to say what is the centroid of this part, let's say this is your centroid, that's equals to that b by n plus 2, say the variation is 2 degree. Say the variation is 2 degree parabolic. If you want to say it's a parabolic, the area for this part would be 1 by third of total BH, and area for this part would be 2 by third of BH, such that overall value becomes rectangle area of rectangle BH, and the centroid for this part would be at here at 3b by 8 from the side that's closer to the centroid. So finally, if you have this curve that such that the loading such that the slope here is 0, but here should be some value, theta not 0, here theta should be 0. So we have that area that this is your 3 and the loading, we can say this is your 2 degree curve. This is your value of that 3b by, no, this is your sorry, if it is your 2 degree curve, then the area is equals to bh by 2 plus 2, bh by 2 plus 2, 2 plus 1, bh by 2 plus 1, that's n plus 1. So the area becomes equals to bh by 3. And similarly, your centroid x equals to that b by n plus 2, that's b by 4. So these two values are very important for your next question. Let's say this is a question that you had a simply support beam for a length of 5 meter, and your variation of that loading intensity is it's a 2 degree variation that W equals to 7x square, and the x is going from this point 0 to 5 meter. So see here, this loading intensity is 0, then it reaches to some value of that 7x square. So your loading intensity is this one. So you need to get that shear force and bending moment. Yeah, shear force diagram and bending moment diagram. So initially we can say that get the reactions. Say this is your support A, support B. Say this is your reaction A, reaction B. We can write A plus B equals to area of that curve. Since your curve is 2 degree, that means we can write that total external load P external equals to area of that loading diagram, that's 1 by 2, no, not triangle, it's equals to BH by 3, BH by 3. So your B is 5, H is your 7x square by 3 by 3. This is your kilonewton, 7x square kilonewton per meter. So your P external becomes 5 into 7x square by 3. So for the value of x equals to 5, we can write 5 into 7 into 5 square by 3. So final value of that total load 291.667 kilonewton. So we can write A plus B equals to this value by summation of forces, and let's say that the centroid of this part, we know centroid is acting at 3b, no, not 3b, it's acting at b by 4. So if you want to say summation of moments about any point, say summation of moments about point B, summation of moments about point B equals to 0, we can write A into 5 clockwise, and this one is your anti-clockwise loading of total 291.667 acting at that x b by 4, that's your 5 by 4, and you get the value of A equals to 72.9167 kilonewton. Similarly, we can get the value of B equals to 218.75 kilonewton. Now we can make the shear force and bending moment diagram. Here the shear force diagram, shear force value of 72.9167, and since at the point B there is a shear force diagram, that shear force value of upwards 218.75. That means there should have been variation such that final value, because of this external load, reaches to the point that 218.75 shear force diagram. And here the value is 72.9167. So the variation is that here the slope should be 0 because your loading here is 0, so your slope here is 0, and here the slope is not 0 because your intensity is 7x square, 7 into 5 square. So we have to join the two. If your variation of loading is 2 degree, that means your shear force diagram is variation is 3 degree. And similarly, we know that the shear force is 0 at some point, say x. We want to get the value of x. For that, we need to get the value of shear force. That we need to cut the section and get the value of shear force equation. Say, if you cut the section somewhere at x, we know that there should be shear force of Vx. Later we would equate it to 0. Here the moment would be mx, and we want to write the general equation, that what is the value of shear force and bending moment diagram. Say this was your reaction 72.9167, so length x. We can write this is also that 2 degree curve. Here the intensity would be that varying with the length, so we can get the value of that. We can write summation of forces in y equals to 0. Then we write 72.9167 upwards, and your area of the loading diagram, that's downwards 1 by 2, not 1 by 2. That's area of that curve equals to PL by 3, BH by 3. So your B is your x, h is your intensity at that point. So intensity at any x equals to, we know that maximum is 7x square. It's for length of 5 meter, but we need for that x meter. So we can get the value of 7x cubed by 5. 7x cubed by 5, and this was your area BH by 3. So and we have that shear force of upwards shear force of Vx equals to 0. And for the condition that we know that shear force should be 0, and for shear force to be 0, we can get the value of x equals to, that comes out to be equals to 3.149 meter. So your shear force is 0 at 3.149 meter from your support A. And now we can get the bending moment diagram also. We can write the bending moment equation, that we can write that 72.9167 for length of x, and your loading intensity was that minus x into 7x cubed by 5 into 3, that's 15. Then after that it acts at the centroid, say at here the centroid from x equals to x by 4. Yeah, then we have negative anticlockwise, mx equals to 0. So here mx becomes 0, that this equation 72.9167x minus 7 by 60 x of 5, x to the power 5. Is it this one? 1 2 3 4. Is it 5? We have that this one was your x. Wait, we have that shear force equation, that we have that area equals to BH by 3. Area was your BH by 3. Your B equals to x, and height was your, we don't know the height. We say that height would be, say, w dash, but we have that equation that w max equals to 7x square in the length 5 meter. If you need it for that x meter, this is your intensity, 7x cubed by 5. Yeah, 7x cubed by 5. 7x cubed by 5, then divided by 3. So if I solve that, 72.9167 into that 15, into that 15, into that 15. Then we can say divided by 7. We got some value. We have to divide it by 1 by 4 power 3.5. Yeah, we got the value 3 point this one, that we got the value that this one is your x power 4, final value of shear force at x power 4. So we can get the value share that x equals to 3.5335, 3.533, 3.5355 meter. So this is your 3.5355. Once you got that, we also can say moment x is a function of that 72.9167 into x minus that 7. We know that the area is your x into 7x cubed by 15, acts as x by 4. Finally you got that 7 by 60, x power 4, x power 5. So we want to say what is the moment value at m equals to, while the shear force was 0, moment at shear force equals to 0. That means moment at x equals to 3.5355. You substitute the values here, value of x, you can get the value that 72.9167 into your x minus 7 by 60 into your x power 5, 193.3496. And moment at, if you want to check the moment at end 0, moment at 0, that is 0 because your support is there. And moment at x equals to 5, that should be also 0. That should be also 0 because your support is that free, that hinges, that roller support. So for the bending moment diagram, this is your 3-degree shear force. So your shear force, that here the slope should be for that 72.9167, and here the slope should be 0 because your shear force is 0. So we had to join the two. This is your 4-degree curve, and then there is a the slope here should be more slopes. There should be some more slope because your that shear force is more here. That's negative. Now we have to join the two. Here the slope is 0. This is your BMD, positive, 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 positive. This was all for your shear forces and bending moments. Now we have next one, next to chapter here. That's we call as deflection of beams. That's called as deflection of beams. That's called as deflection of beams. That's called as deflection of beams. Till now, in our shear forces and bending moments, our concern was to get the internal loadings. Internal loadings, that's shear force and bending moment. There is also internal loading of that twisting moment and axial force. Now, for your beams, say we say that for the beams that bending is predominant cause, bending is the major cause, for your deflections, So we ignore the rest three effects. We say that the deflections, because we are dealing in the elastic limit. That we don't want that 100 mm bar to go. We don't want that 100 mm bar to go increase by 1 mm, 0.1 mm. So this is your limit, and out of that, bending is predominant. So you can see what is the effect of others also. And if you want to say for the trusses, if you have truss member, we say that the axial force, the internal axial force, the internal member force, which we calculate, then we cut the section, we say what is the internal member force. That's your actual internal member force. Internal member force is predominant for deflections. So let's say you design a structure that whose strength is good, but it may fail in deflections. Say most of the bridges, they fail in deflections because they had some permissible, delta permissible limit, but because of the design, their permissible limit was crossed because of those loads, because of the external loads. Their serviceability, that we call as serviceability limits, was not ensured. I think we should wind up this class. We will be dealing the deflection of beams in your next lecture.